Hello everyone. In this video we are going to draw the Root-Locus plot for a system given with the transfer function as s plus 2 over 3 times s squared. The controller is in the form of a proportional controller again, so gc of s is equal to kp, and we are supposed to draw the Root-Locus and compare it with what we could get with Matlab, and we also need to determine the range of values for kp such that the closed loop system is bi-Boy stable, and compute if possible the value of kp such that the step response of the closed loop system using a second order approximation is critically damped. So we will see whether it's possible or not, and if it's possible, what will be the value for kp. Alright, so as usual we start by forming L of s, which is equal to kp times s plus 2 over 3 times s squared, and we can rewrite it as kp over 3 times s plus 2 over s squared, and this is equal to rho over rho times s plus 2 over s squared. So we have rho equal to kp over 3, just keep note of that, and then we have n equal to s plus 2 the numerator, and d is equal to s squared. This will tell us that n lowercase n is equal to 2 because we have 2 poles, and m is equal to 1 because we have 1 0, and r, which is equal to n minus m, is equal to 1, meaning that we will have 1 asymptote. N equal to 2 also means that we will have 2 branches for positive locus and 2 branches for negative locus. And m equal to 1 means that one of the branches will end up at the 0 and the other one will go towards infinity, using the asymptote that we need to figure out its properties. So since we have one asymptote, indeed there is no need to find out xa, but we can find it out, and we also need to determine the angle of the asymptote with the real axis. So let's start by preparing the S-plane for each of the positive locus and negative locus. Real axis, imaginary axis, this is what we are going to use for positive locus, and we have it here for the negative locus. For the open loop system, we have 1 0 at s equal to minus 2. So let me first write it down. So n of s equal to 0 means that s1 equal to minus 2 is the 0 of the open loop system, and d equal to 0 means that we have 2 zeros at the origin. So 2 poles at the origin. So 1 0 here at minus 2, and 2 poles here at the origin. Now let's go back to finding the asymptote. If you want to find out the xa, which as I mentioned is not important for this example because we have only a single asymptote, we need to find out sum of zi's minus sum of pi's over n minus m. N minus m is equal to 1. For pi's we will have 0, and zi is equal to 2, so 2 over 1, which is equal to 2. And for the angle of the asymptotes, we have r times kca. R over here is again equal to 1, which is equal to 2h plus 1. With h equal to 0, it will be equal to pi, and 2h pi will be 0 for positive locus and negative locus. So I can draw the asymptote for both cases. let's say we start from here. For the positive locus, the angle is equal to pi, so this will be our asymptote. Sorry if I didn't draw it precisely. Okay, so this is one asymptote, and for the negative locus, we will have the asymptote in this way. So again, this is asymptote. Similarly here. We have the asymptotes drawn. We can now have a look at the parts of the real axis that belong to the root locus. We can divide the whole real axis into three segments, from minus infinity till minus 2, from minus infinity till 0, and from 0 till plus infinity. And if we count the number of poles and zeros to the right side of each region, we will get 3 for the first segment. This is from minus 2 indeed, not from minus infinity. 2 and 0. Okay? And we can see that the first segment will belong to the positive locus, and the other two segments will belong to the negative locus because they are not odd numbers. Let me highlight that in our drawing. So from minus infinity till minus 2 will belong to the positive locus, and the rest will belong to the negative locus. Okay, so we have determined in the parts of the real axis which belong to our root locus. Now we know that, and we also know that the branches will originate from the open loop poles of the system. Okay, so that's some information that we already have. If we look at the positive locus one, we can see that if we have branches originating from the poles at the origin over here, they should go out of the real axis immediately because they cannot continue on the real axis, as the real axis around that area doesn't belong to our positive locus. So for sure, for the positive locus, we will have break away point at s equal to 0. They will break away, and at some point they need to come back to the real axis, because then one branch will approach the 0 at minus 2 and the other branch will go towards minus infinity. So there will be some break in point between minus infinity and minus 2 that we need to determine the exact value. For the negative locus, on the other hand, we can see that the two branches that will originate from the poles at the origin, one will move towards the 0 at minus 2 in this way, and the other one will move towards plus infinity on the real axis using the asymptote. So there will be no break in or break away point for the negative locus. If you remember, to find out the break in and break away points, we need to find out m prime times d minus n times d prime equal to 0. For n we have s plus 2, so n prime is equal to 1. For d we have s squared, therefore d prime is equal to 2 times s. If we plug those values into the equation that we have over here, we will have s squared minus s plus 2 times 2s equal to 0. For this equation, one root is equal to 0. So s is equal to 0 is 1, solution, and then the other one will be s minus 2 times s plus 2 equal to 0. And from this we will get minus s minus 4 equal to 0, and this will give us s equal to minus 4. So s equal to minus 4 and s equal to 0. We know that s equal to 0 is the breakaway point already. And then s equal to minus 4, which logically lies in the real axis which belongs to the positive locus. Let's say it's over here, minus 4. It will be a break-in point. So this is break-in point for us. Well, then now we know that the branches will depart the poles at the origin. We can find out the angle of departure. So alpha departure should be determined here. They will enter into the break-in point at minus 4. Then one will move towards the 0 at minus 2, and the other one will move towards minus infinity. We will have some kind of graph like this. And for the negative locus, it's kind of obvious what we have. So let's check out how we can determine the angle of departure. You can either refer to the formula that we have, or you can apply the phase condition in the vicinity of the poles for which you want to figure out the angle of departure. Okay, so let's say that we have a test point pretty close to the poles at the origin, for which we want to find out the angle of we want to apply the phase condition. Okay, phase condition tells us that phase of n over d is equal to phase of minus 1 over rho. We are going to do it for the positive locus. For positive values of rho, this will be equal to 2h plus 1 times pi. Okay, for positive locus. Phase of n over d could be written in the form of phase of n minus phase of d evaluated at s star. And to find out that for n of s we have only a single 0, if I want to find out the angle contribution of that 0, this is the approach. We connect a line from that test point to the 0, and then we draw a horizontal line from 0 towards plus infinity. And the angle that we get here will be the angle contribution from the 0. If the test point is pretty close to the origin, this angle will be 0 degrees. Okay, so we will have 0 minus, for the angle contribution coming from the poles, let me use another color. We will have this angle, which is actually the alpha departure, and we have two poles, therefore we will have 2 times alpha departure, and this will be equal to 2h plus 1 times pi. Since we have two poles over there, we will be able to find out two departure angles, and therefore h should be set to 0 and 1. With h equal to 0, we will have alpha departure equal to minus pi over 2. With h equal to 1, we will get alpha departure equal to minus 3 pi over 2. And now if we go back to our graph, we could see that the branches will lie on the imaginary axis right at the beginning. The angle of departure will be equal to minus pi over 2 and minus 3 pi over 2. And therefore so this is not very neat, but I guess you got the point, yeah? They will enter into the real axis at the point minus 4. One will go towards the 0 at minus 2, and the other one will move towards minus infinity. And for the negative locus, for this example, it's pretty straightforward. We will have this and these branches. Alright, so we are kind of done for this example. There's no need to calculate the angle of arrival at the zeros. You can do it for this 0, but it is kind of obvious, yeah? For this one it is 0, for this one it is pi. You can still apply the phase condition in the vicinity of that 0 and figure out what will be the angle of arrival. But obviously there is no need in this example. Okay, now we can have a look here. Find the range of values of Kp in R such that this closed loop system is biboy stable. If you look at the positive locus, we can see that for any value of rho bigger than 0, the system is biboy stable because the poles are on the left half plane. And for the negative locus, for any value of rho smaller than 0, the system is not biboy stable because we have one pole always in the right half plane. So the range of values for rho for which the system is stable is rho bigger than 0. We will have a biboy stable system. And since rho is equal to Kp over 3, this means that for Kp bigger than 0, we will have our system biboy stable. The next point is to check whether our system could be critically damped. In the case of critically damped systems, if you remember, we have two poles at the same location on the left half plane. If you look at our graphs, it's not possible to have it with the negative locus. But with the positive locus, we can eventually have it. We can eventually have two poles over here. I'm just highlighting it. For which we can determine the value of rho. So let's see how much will be the value of Kp or rho over here. I assume that by now you know how to do it. You can apply the amplitude condition. At that point, we already know that that point belongs to our Root-Locus. For n of s, you can either plug the value of s, which is minus 4, into the equation. N of s is equal to s plus 2, so we will have minus 4 plus 2 over minus 4 squared. And this will give us 2 over 16, which is 1 over 8, and it's equal to minus 1 over rho. Therefore, rho will be plus 8 because rho is positive over here, and Kp will be equal to 8 over 3. In this case, we will have two poles exactly at the point minus 4, but keep in mind that this system has a 0 at minus 2, so you cannot say that the overall system could be approximated as a second order system, as a critically damped second order system. So we can't have that exact approximation, but if you want to have the closed loop poles at the point minus 4, this is the value of Kp that we need to have. Okay, 8 over 3. We also need to compare our results with what we can get from Matlab. So these are what we have obtained, and over here I also have drawn the results that we could get with Matlab. This is what we have for the positive locus, and here we have it for negative locus. You can see that it looks like the one that we have obtained for the positive locus. The branches will originate from the poles at the 0. The angle of departure is equal to minus pi over 2 minus 3 pi over 2. The break-in point is exactly at minus 4. Then one goes towards the 0 at the on the real axis at minus 2. The other one goes towards minus infinity. And similarly for the negative locus, the branches originate from the poles, open loop poles at 0. One goes towards the 0 at minus 2, and the other one moves towards plus infinity on the real axis. So what we get with Matlab is consistent with what we have obtained manually for the Root-Locus plot. Alright, so that's all for this video. Thank you for watching, and see you in the next video.